Now we come to BASF, and I think we all are aware that it's the largest chemical company of the world. So if they deal with the smallest reactor, that is interesting to hear. And I have to give credits to BASF. They were actually, I think, the first chemical company who was involved. With our friends in the Forschungszentrum Karlsruhe at that time, and also with my institute. That was as early as '94, if I remember correctly. And the big figure here, I really have to name for those who know a bit IMRET, is Otto Wörth at BASF, who was very visionary to put big bulk chemical processes into those small reactors. And not everybody could understand that at that point of time. And I'd like to hear now from Christian Holtze if that has changed a bit. He is a principal scientist, flow chemistry at BASF. He studied chemical engineering at the Technical University of Berlin and at MIT. He graduated in physical chemistry from the Max-Planck-Institute of Colloids and Interfaces. I think that's also next to Berlin. He worked on microfluidics during his postdoc at Harvard University, and that is where Daniel Weitz is, so that is an excellent address. And in 2007, he joined BASF, and he implemented microfluidics into BASF corporate research with a focus on formulation and screening. Christian is dedicated to interdisciplinary and holistic product development, and he leads whole teams of engineers and physical chemists. His interest shifted then a bit, if you know the difference, from microfluidic formulation to flow chemistry. That's what we are here about. Also, we are also open to microfluidic formulation. And he took the role of BASF academic partnership developer for his strategic partnership with Imperial College in London. And over the years, he has built in this way a large international engagement. So Christian, go ahead for the next 25 minutes. Thank you.
Thank you very much, Volker. Good morning, everyone, and good evening to Australia. It's my pleasure to give a talk that I hope will be complementary to what Sebastian just presented. And I'm going to build on his last statement that we should assume a holistic view on flow chemistry. I'm going to mainly focus on change management in order to make flow chemistry a widespread and widely deployed technology in the industry. And I'm not going to talk so much on engineering achievements. First of all, I would like to define two terms. I think when you're operating a microreactor in continuous mode, then integrate that into a process, then we're talking about flow chemistry. And flow chemistry in terms of BASF would be any continuously operated process on a scale that's smaller than world scale commodity. So we're talking about specialty and fine chemical production, including agrochemical production, the actives. And in particular, I will be focusing on the R&D stages of using continuous processing. Just a glimpse about BASF. We're a very large company, which is not too well known to the general public outside of Germany because we're mostly doing business to business. Our sales were 60 billion last year, despite Corona. We're about 110,000 employees worldwide, and we invest 2 billion euros per year into research and development. With that size, a couple of challenges come about, and that's with 10,000 employees in research and development, there is a large degree of specialization. And specialization doesn't always help the cause. And also there is the requirement for a lot of communication with 3 corporate research divisions, plus a department in digitalization, plus hundreds of collaborations worldwide with sites in every part of the world and 12 business units. BASF is a very tough organization to drive change. And well, change is required, we think, because for decades it's been shown that there are many undisputed benefits to flow chemistry. It's been shown that there is continuous processing expertise at the word scale at BASF. So why would we be reluctant to using it on any small scale that is smaller than word scale? And there is best practice available, mostly from the pharma sector. So we started out by asking ourselves the question, why is flow chemistry not widely applied in R&D and in specialty chemicals production at BASF? And the first question, of course, you have to ask is, would it even fit BASF's strategic goals? And those goals are around sustainability, and sustainability can be seen in three different parts depending on what you're talking about. One is CO2 footprint. The second one, mostly in the materials business and polymer business for BASF, is around circular economy. And then you have collateral environmental damage, for example, for agricultural actives, but also for solvent use and synthesis. A second part would be process safety. And there we're talking about hazard potential and inherent safety. And the third one is, of course, our economic purpose. Processes need to be economical and competitive in the chemicals production market. Focusing on sustainability, we think that flow chemistry has a lot of value in chemical conversion. It has been demonstrated in hundreds of examples to yield more product and to be more selective than batch processing. It bears the potential of making renewable raw materials amenable to chemical processing. And by smart and challenging chemistries, we may reduce the number of synthetic steps to arrive at a desired molecule. That's called step economy in our business. In terms of safety, we're looking at a number of key values. One is, of course, related to the smaller hold-up volume of a flow reactor compared to a batch reactor of similar productivity. And the other one is very much driving into the direction of microreactor technology about intrinsic safety. In terms of economical value of flow chemistry, we're confident that we can have the same low specific investment, that's the euros of investment per ton of capacity that you have to do, as in word scale processes. We're confident that we can have benefits with respect to operating expenditures by saving labor in a continuous process, by saving synthetic steps in order to get to the desired molecule, and by improved product consistency. In terms of transportation, distributed manufacturing might be a future avenue. And in terms of flexibility, numbering up, and the modularity that we've just heard from Sebastian are certainly avenues to be explored. Now that we've set that flow chemistry actually does make sense for BASF and fits its strategic goals, let's look at what the root causes and hurdles to implementation are. And I will then move on to suggest a competence-driven approach. And in doing so, what I'm going to talk about is mostly the R&D phase. Because in looking at the deployment of flow chemistry, there is one particular milestone, and that's the investment decision. If you're managing your R&D process to get to a positive investment decision, then you're carrying flow chemistry into production. And then plant operation and commercial use are going to follow. let's look at the challenges that need to be overcome in the deployment of new technology in general, and that holds true in particular for flow chemistry. And I've subdivided these into know-how challenges and infrastructure challenges. The first set is related to cost. And of course, it costs money to educate people and build up competence. Failure is cost intensive, and it costs money to invest into the assets that you need in order to perform flow chemistry on a lab, pilot, or production scale. Risk is something that is a major consideration in management. Will the technology pay off, and will it be accepted? What about asset utilization, and what do we do if we need to react flexibly to changes in the market? Then there is an individual dimension. One is about the personal competence. Do I know when and how to apply flow chemistry? And do I have access to fully equipped facilities? If I have to wait for a pump for 4 weeks until the order has been processed, then I'm not flexible, and that's going to slow down my R&D. And the final set is around organization. How do I set up a seamless R&D workflow? And how do I generate best practice and workflows for scale up? So handover, that's a major organizational challenge. If we're condensing that into the challenges that we need to tackle, it's challenges around the infrastructure, around competence, and around communication. And that all is going to build up to the workflows, both on the personal individual side and on the infrastructural side. In translating that into actionable measures for flow chemistry deployment, we need, of course, to establish technological solutions, provide appropriate infrastructure. We need to generate best practice in order to be able to quantify the risk and build confidence. And we need to set up communities that will allow for a seamless and holistic workflow. Now, the way we're tackling this, and I don't know why the half of my title is hidden, is about addressing the key challenges in strategic collaboration with academia. Why would we go external? That's the first question to answer. And our take on that is there is competence outside of BASF that is complementary to our expertise. And it's good to bring these competencies together in order to drive new and disruptive technology. The setup needs to be interdisciplinary. And we've chosen a setup of a PhD cluster, which is going to deliver impact only in the midterm. So we're going on a journey of change management, and that's why we're selecting the format of a PhD, which takes about 4 years to start with. Then funding, we're hoping to tap into leverage funding opportunities, especially if we're looking at the early technology readiness levels as opposed to Sebastian. We've selected a bespoke setup. We're focusing on Imperial College as our partner, and that gives us access to excellent talents and infrastructure. We're assuming a mindset of co-creation to develop our technological capabilities, and we're engaging in a strategic partnership. And the way I would define strategic is that we're sharing the vision of how we want to make research have an impact in industry. And that's going to help us tackling the challenges I mentioned before. Now, we need to bridge the gap between industry and academia. And we have to realize that there are different motivations. In industry, it's about making money, innovating products, building and operating plants, selling products. And it's about saving time because time is money. In academia, it's about generating understanding, discovering. It's about interesting effects and more pronounced you're going to see these differences in publishing confidential information, there industry and academia have opposite views. So it is important to align, to combine the opportunities that industry holds in terms of impact and that academia has in terms of coming up with great ideas and understanding. And that's what we need to align in order to make research have an impact. The shared vision that I just talked about. The atmosphere in coming up to that point of aligned goals, strategic vision, is about co-creation. And I would call co-creation something where an academic and an industrial scientist talk on eye level, with respect both on the scientific level and on the personal level. And they need to have fun, of course. Collaboration is a thing that is a partnership, an individual way of interaction. That brings me to interaction. I think that driving flow chemistry toward a widely deployed technology in industry requires building and connecting communities. It requires mirroring the expertise in industry with the expertise in academia and vice versa. And it requires a holistic and interdisciplinary approach, and that's what I'm going to talk about right now. Holistic means that we're considering the whole R&D workflow, which is generally starting out in the lab with a proof of concept experiment that I can have the desired chemical conversion in my flow reactor. Then we're inevitably going to go through a screening and optimization stage before we enter into the pilot scale. And on the pilot scale, you have classical reaction engineering challenges like reactor design and scale up, but you also have additional safety requirements. And in designing a flow chemistry process, you will need to integrate separation units into your consideration. And we're looking even ahead in order to prepare everything we need to have in hand for the investment decision to be positive. We're looking at techno-economical benchmarking, value and supply chains, and like. In parallel, we're setting up infrastructure at BASF, and we're preparing for the transfer, which is already taking place during the early stages of a PhD by aligning visions, bi-weekly telephone conferences, and is going to be carried out in the form of 6-month placements to BASF in the later stages of a PhD. And with that, we hope to build the competence to and have the information available to take a positive investment decision into a flow chemistry plant and eventually operate the plant. In terms of interdisciplinary approach, we're convinced that we need to combine the chemistry, the chemical engineering, and the business as a holistic and interdisciplinary approach. There is an underpinning technology, which is the digital methods centered around machine learning and data science, but also multiple other things, starting out with modeling, going through computational fluid dynamics, all the way to value chain optimization and in production, even predictive maintenance. So with that, we've designed a vision of a holistic and interdisciplinary approach. But how do we realize that, and what are the hurdles, the valleys on our way to industrial deployment? There are multiple dimensions where things can fail. One is certainly along the R&D workflow. It is not natural that people in the lab know how to communicate with people in the pilot scale, and those might have completely different opinions than people in production. The same holds true for interdisciplinary approaches. chemistry, chemical engineering, digital, and business people speak completely different languages. There is cross-departmental issues to be resolved in two big organizations, BASF and a big university like Imperial College are separated into departments, and usually that results in organizational hurdles that need to be overcome and sorted out. Then, of course, we have many stakeholders at different levels of hierarchy. A technician that operates the machine speaks a different language than a scientist. And of course, the scientist needs management to buy in, so appropriate communication with management in order to realize what he perceives as an opportunity. And finally, if we're partnering with academia, we need to somehow coordinate coordination between professors, students, industrial scientists, and industrial technicians. So we need to find a way of communicating between each other. And communication is really the key. And in times of Corona, we're facing that there are some additional hurdles. Nonetheless, we've managed now to have 2 flow chemistry conferences at BASF, bringing together all the stakeholders from management and industrial scientists, professors, and students with a variety of interdisciplinary backgrounds. Now, I would like to wrap up with 2 slides on where we think it is best to start out doing flow chemistry. It's about balancing. We cannot tackle everything, and BASF's view on flow chemistry might be different from GlaxoSmithKline's view of an end-to-end flow chemistry process. We think that typically you will want to have 2 to 5 telescope steps in order to reduce process complexity and improve flexibility. Also, in terms of modularity and investment, BASF assumes a fairly pragmatic view on specific bespoke processes versus multi-purpose, flexible, modularized processes. We think that it has to be a case-by-case decision. Standardization is very much the same. Do we need specifically designed kit, or do we use off-the-shelf equipment? And eventually, the investment is a decision that will be taken for every single process. Can we use our depreciated batch facilities, or can we imagine investing into a new flow chemistry process? Overall, the future development of flow chemistry is, according to my thinking, going to be supported by a number of trends that are in some cases quite unrelated to flow chemistry, and that tap into every single stage of the R&D workflow. These trends are around self-optimizing systems. They're around process simulation using digital methods. They're around digital twins all the way to decentralized production. We think that there is a number of developments going on that will boost flow chemistry deployment in the next years. With that, I would like to conclude my talk. I started out by checking and confirming that flow chemistry holds great promise for BASF's strategic research challenges. I think, and that's our opinion, that coherent, holistic R&D concept is required, comprising infrastructure, competence, the communities, and therefore the entire workflow. We think that complementing our internal expertise with external partners in academia is the right way to go. for a holistic, interdisciplinary, and stakeholder-oriented way in which we need to take good care that communication works well. The future will show how we can balance the different requirements, and we're going to benefit from complementary trends. And now I would like to stress one of Sebastian Hettner's points. We think that an efficient R&D workflow is possible through flow chemistry. We think that it will be possible one day to consider the requirements of later stages of R&D very early on by bringing in expertise from engineers and from modeling and from process simulation to the early stages of laboratory. But that requires a change in mindset, an openness, and change management in the organization. To achieve that, we would be very happy to partner with different universities around the globe and different commercial entities around the globe. If you have an idea, please reach out to me. Thank you very much.
Thank you so much, Christian, for this excellent talk and for giving the good news academia still needed and much needed. That is excellent to hear and clear to me, but maybe not to everybody, how much you have to convince that technology development is maybe the minor part, but winning the hearts is the major part. Tosh Folios writes an excellent talk with respect to relationship with Imperial. How is the need for a PhD student to publish balanced with IP generation or confidentiality? So how do you balance this, publishing and IP?
Generally, we're hoping to file a provisional patent and then be free to have the clearance for a publication. That's how we're currently doing that in 2 cases, and it's worked out. There is a 150-year track record of working between BASF's corporate research and academia. Fortunately, our organization is very well aware of the need for academics to publish.
Great. A question from Christian Hornung, he also says, great talk, Christian. And he asked about the techno-economic analysis, which you do. At what stage does BASF use those analyses? I mean, you can use it early, ex ante, to look if something is costly and to identify hotspots, or you can do it later to verify it. There are 2 ways to do it. What does BASF do?
So currently, the most involved way of doing techno-economical analysis is by a proprietary software called ChemaSim, which is a flowsheet modeling process simulation software. It is quite evolved to estimate both cost and sustainability aspects, but it requires a lot of data. Our current development in collaboration with academia is driving toward making a qualified, somewhat informed decision at an early stage, which of the alternative routes to pursue. So I think there is room for future development and also for academic contributions into something that is really at the heart of a commercial company.
Yeah, thank you. I'd like to give you a question because we still have time, and I'd like to motivate the attendees also to give a question, and I give them time by giving my question. The last word you said, that is for me the most important because I work on that and I love it, decentralized production. I mean, a company like BASF who has everything on a large footprint, and I was in Ludwigshafen, why do you argue for decentralized production and where will it happen?
So, people generally move to these Verbund sites, the network sites like Ludwigshafen with 40,000 employees and 20 million tons of product per year, because heat integration and mass flow integration and safe transport through pipelines from chemicals from one plant to the others were just so convenient. Our current turmoil in the COVID crisis, supply chains being disrupted, and globalization facing major challenges, show that some level of decentralized production will be required. I think the boundary conditions we're always going to have to face are logistics. If we need to transport chemicals, we need to make sure that the transportation of raw materials to the site of decentralized production is somehow balanced with the transportation savings of the product. And another thing that we need to worry about is, of course, the integration of the process with respect to heat integration in particular. Does that answer your question?
That answers my question. Let me give you a last talk from the attendees, and sorry if I missed one question there, I saw it. The question is from Ivan. He said, do you incorporate continuous steered tanks in flow processes, or have you considered it? Very interesting question.
Indeed, I think when you're facing an increase in viscosity or solids formation, CSTRs and cascades are a very, very good option to consider.
Then a very quick, but that's really the last question from Peter Pöschelauer, who talks tomorrow. He says, also great talk. If digital retrosynthesis is at the start of your synthesis consideration, where would you expect unexpected and inventive chemistry come in? Maybe with a quick answer.
I think the unexpected is really something for academia to think about. If industry can speed up their development by building on published literature, we're happy because we're going to be quicker at deploying flow chemistry.
Okay, yeah, maybe it comes from biomass and CO2 because we are not so familiar still with those processes. Okay, thank you so much. I think that was a very good talk and also a very good question answering session.